I want to talk to you about ideas. Where do they come from? Well, I'm sure that ideas do not arise the same way for everyone, but I'm going to tell you about how they come to me. I think that I have been very prolific with ideas, and I want to tell you about some of the good ideas I have, and about the best ideas I have now. Ideas from nothing. What you need is inspiration. You need to think differently. You need something that makes you think differently. How can you make yourself have ideas? How can you force them? There are no overnight successful ideas. Ideas take a long time to develop, to synthesize. It is hard work. Using biology for inspiration is itself a great idea. We just need to think differently. For now, we are seeing biology as a powerful mechanism for thinking differently. So I'm going to talk about biologically inspired systems engineering, ideas from nothing. Here is what I want to talk to you about today. I'm going to start off and talk about my origins, of course we're a sum of our parts. Then I want to talk to you about some big ideas, theories of mind, surrogate modeling, and self-similarity. And then I'm going to come back and talk to you about how we can get ideas from nothing. I grew up in the Southern Hemisphere. This is the Milky Way, a part of the Milky Way that you cannot see from the Northern Hemisphere. The Milky Way is much brighter in the Southern Hemisphere. When there is a new moon and no clouds, it is almost as bright as if there was a full moon. I was listening to National Public Radio one day, and a female reporter was interviewing an Australian astronomer. She asked him why the sky was so much brighter in the Southern Hemisphere. He replied, "It is like this, mate. We are looking right into the guts of the Milky Way. In the Northern Hemisphere, we are looking the other way, out of the Milky Way. In the Southern Hemisphere, you can also see other galaxies with the naked eye. Here, the Milky Way is the bright diagonal across the screen. That little stripe on the right, just below halfway up, is the Large Magellanic Cloud. In the bottom right corner is the Small Magellanic Cloud." I grew up in Australia, on the Gold Coast, just south of Brisbane. It is on the east coast, about the middle where Australia sticks out the most. The Gold Coast has many towns, which were separate villages once, but are now connected. This is a picture of Surfers Paradise. I spent my teenage years living in Surfers Paradise, and that is still what I regard as my Australian home. The climate is great, the surfing is great. The Southern Hemisphere has a much milder climate than the Northern Hemisphere. The extremes of weather and temperature are much less. That is to do with the way the Earth tilts when it goes around the Sun. That is my brother surfing at Surfers. The board just gets longer as you get older. What a great wave. There is an area on the Gold Coast where wild parrots land on you, as long as you have some food. They do not do it anywhere else. The most important work I have done in my academic career is related to roadside bombs. This image is from a training exercise and no one was hurt. Since 9/11 we have all been confronted with terrorism which shook us to the core. Most of us recall with absolute shock. Let's hope we never forget. From 9/11 plus one day, I was committed to doing something that would address this problem. My biggest problem was that I did not know what to do. What problem could I possibly work on? I knew I was good at some things. I had a very good understanding of how electromagnetic fields and circuits interacted. I kind of knew how these would interact with systems. I had the inkling of an idea, a problem set worth working on. How can we locate all the electronics in our environment? But there was not enough to address the problem. Well, when the US forces entered Southwest Asia and encountered improvised explosive devices, that is IEDs, I knew then what I had to work on. I was going to find a way to locate electronics and to stop electronics from working. The good news is that I had a problem to work on, but I needed ideas. That is what I'm going to talk about, creating ideas, the key ideas I had, and these are still my best ideas. The best thing I ever did in this whole IED space was making people think differently. That is what made the difference. One of the technical highlights from the work done 5 to 10 years ago is that we developed the ability to measure smaller signals than anyone else could. In particular, we developed techniques for measuring small radio signals that are very close in frequency to other radio signals, large radio signals. If you have two radios next to each other and one is transmitting, it can be quite difficult for the neighboring radio to listen. The listening radio is trying to respond to very small signals, but the transmitting radio is sending out very large signals. With cell phones, this problem is solved by separating the frequencies of the transmitted signal and the received signal by a very large amount. Then we use devices called filters to separate these signals. But there are situations where you need to transmit and receive at the same time, and these signals are very close in frequency. In my lab, we can do that 1,000 times better than anyone else. We have transferred our technology to many defense labs and companies. When we built something and delivered the technology, that was applied research and technology transfer. However, this was fundamental research as well, as it enabled us to understand how electromagnetic fields and electronics interacted. This work led to the 2010 Microwave Prize for the best paper on microwave engineering in any IEEE publication. We were doing work that was very applied, but it was very fundamental at the same time. In fact, our experience has taught us that fundamental research, applied research, technology transfer, and extension are all much the same thing. Here's an example of a result no one could look at before. This is a measurement of the electrical signals on a vibrating antenna. This could be an antenna on an aircraft that is vibrating tremendously. Here we are transmitting a very large signal, yet we are receiving these other signals. These other signals are coming from the vibrating antenna. We have shown that this is a relativistic effect, kind of like the Doppler effect. Previously, these small signals could not be measured. However, in a radio receiver they would create interference, and an intended signal could not be received. As well as working with electromagnetic fields and circuits, we also do a lot of acoustics work. This is a high-power speaker that can blow eardrums out at 100 meters. We use this speaker to shake objects, and then we can use a laser or a radar system to measure how much something vibrates. If you know how much an object vibrates and how it vibrates, you can tell objects apart. You could tell if you have a fiberglass shell, which is shown on the top left here, something you could put over an outside faucet, or perhaps you could hide something inside it. You could separate that from the concrete block on the top right, or identify a fake rock as shown on the bottom left. This fake rock could be used to hide an improvised explosive device. It looks like concrete, doesn't it? But it is dry concrete over foam. You also need to know if what you are looking at is just a rock. What we really did that was most significant is that we developed ideas. The ideas that we developed led to an Army medal. Over the years I have worked on many research projects, primarily funded by the U.S. Army Research Office, NSF, and the Office of Naval Research. However, I've done projects for many agencies. I have been lucky, I guess, as 85% of the proposals I have written have been funded, for a total of about $34 million. I think that may be because my proposals are much more than a work description. The proposals are rich with ideas. These ideas have the broader impact. Yes, there are technical specifics identified, but it is the broader impact that captures people's imaginations. In the last decade, 5 of my PhD students have begun startup companies, and I'm going to talk about 3 of them. Greenwave Scientific, started by Mark Buff in 2008, makes military antennas. Vadem, started in 2004 by Aaron Walker, works on electronic warfare. Look at one of their news items from October 2013. This says that they just received a $9.8 million contract for research and development in electronic warfare. This startup company is making a difference in our region, and it is contributing to national security. Mohu, started by Mark Buff in 2010, is now the leading manufacturer of HD TV antennas. They employ 60 people in North Raleigh, and that is where they do all of their manufacturing. Their products initially were the commercialization of military antenna technology. Currently, my team is very interested in energy localization. What is shown here is a computer model of a homemade explosive. The explosive consists of explosive crystals embedded in a medium, the plastic in plastic explosive. Here we directed an electromagnetic wave, a radar signal if you like, into the block from the bottom. The red areas are where the energy localizes. The reason we are interested in localizing energy is that if the conditions are right, the explosive will burn and melt rather than explode at those hot spots. Now this is a computer model. It is fairly painful to place those crystals. So how can you automate it? You turn it into a computer game. These are crystals being poured into a container. They assemble themselves. With all of this work, I've become quite passionate about national security. As promised, I'm going to give you my best ideas. The first is about the theories of mind. What a great painting. Why do we like paintings like this so much? I'm going to have a go. I'm going to be very different from the classic art critic. That's okay, I don't care. I do think that this is a great inspiration for ideas. Another great painting. This is Jackson Pollock's number 11, also known as Blue Poles. It's in the National Gallery of Australia. So what? These paintings tug the internal workings of the brain, but in two very different ways. Both provide great biologically inspired ideas that tell us a lot about how the brain works. An idea of how the brain works is called a theories of mind. So there are many theories of mind. One of the theories of mind is that the human brain is forever trying to fit models to experiences, continuously refining the model fit. We anticipate, make model projections, usually without being consciously aware. Now, President Obama didn't say this, but he's a very smart guy, and I think if he'd thought of it, he would have said it. In my proof that President Obama is a smart guy, I need to introduce you to the secret handshake of electrical engineers. This is Fleming's right-hand rule of electromagnetism. So get your right hand out and put it in this form. The thumb is pointing in the direction of the electric field, the magnetic field is in the direction of the index finger, and then the middle finger is in the pointing direction, the pointing vector direction, and that is the direction in which electromagnetic fields travel. So if you're walking down the street and you make that virtual handshake, and if another electrical engineer sees that, they'll say, "Hey, you understand electromagnetism, and electrons are green too." Now, President Obama is a really smart guy, and here is a picture of President Obama teaching Fleming's right-hand rule to locals. Keep your fingers arranged as I said before. Now I'm back to talking about theories of mind, and let's pick on something. We'll pick on the way hearing works. So sound enters our ear, and somehow or other we're able to get meaning from those vibrations of air. Now listen to what I'm going to say. Ba, ba, ba. Ba, ba, ba. Ba, ba, ba. Ba, ba, ba. In the first segment you probably thought I said ba, ba, ba. And in the second segment with the video you heard me say da, da, da. But in both cases I was saying ba, ba, ba. I just used a different video. Now what was the mind doing there? The mind was taking input. When it just took an audio input, it did the best job it could, and it determined that I was saying ba, ba, ba. But in the second case, when we had an additional input, a visual input, we were able to fit a better model to what I was trying to say. There was one model that thought I made the sound ba, and another model with more input thought I was making the sound da. And in the end, the illusion is that the brain tends to vote for the sound da, and that's what you hear. An idea, a theories of mind, is that the brain is always fitting models. This is a model. Here the X's are the inputs and the output is meaning. So the brain is always developing these models, updating these models, and extracting meaning from the input. A theories of mind is that the brain is fitting perhaps 10,000 models to our experiences all the time. So when we're listening to somebody speaking, we're trying to fit models to what they're saying, we're trying to project what they're saying, we eliminate the models that don't seem to make sense, and we continuously refine those models. The brain is perhaps fitting 10,000 models at a time and selecting that model that has the best fit to the experience. Sometimes it's not enough to listen to one word, we have to listen to a whole phrase, and we do this all the time. So there are many models. Here there are 500 models. For 10,000 models we need 20 pages like this. Gosh, that is an idea. Perhaps when we solve our engineering problems we should not try to come up with just one answer. Perhaps we should come up with the best 10 or 100 answers. Perhaps we should look at 10,000 answers and pick the best few from that. Here is another idea. This is surrogate modeling, but these ideas are all related. This is a picture of the Warrangamba Dam, Sydney's water supply. Engineers need to model the dam and be able to predict water levels, for example. When we develop a model of the dam, we want to relate inputs and outputs. Our inputs could include rainfall history, air temperature, various sensor inputs such as the soil moisture and the height of the water at the moment, the nutrient level, and the age of the dam, which gives us an idea of how much sediment is on the bottom of the dam. Our outputs could include water height, predictions of the water height, water temperature, suspended sediment level, volume, dissolved oxygen level, nutrient level, and evaporation rate. So our inputs are the X's, X1, X2, X3, and our outputs are Y1, Y2, and Y3. So we want to be able to predict the state of the dam given the inputs. So here is our model again, with just the X's on the left and the Y's on the right. We could have a very elaborate computer model. This would be our fine model. It is not the real world, it's still a model of the real world, but it's the best model that we can possibly come up with. This computer model would take an enormous amount of time to develop. We'd have to continuously refine it, lots of resources go into it, takes years and years to get the model right, and then if anything changes we have to update the model, and then if we want this model to work with another dam we have to go through another exercise of developing and fitting and adjusting the model. A coarse model, which wouldn't take a lot of effort to develop, would be a bathtub model. The input is the rainfall, it comes in through our tap, our faucet. We have sunlight which heats up the water and there's evaporation from that model. So this model wouldn't take a lot to develop and it possibly applies to all dams. This would be our coarse model. We have our X's going into a coarse model which is described by just a few equations and we have the outputs Y. But it's not a very good model. But it gets the essential nonlinear characteristics right. So the Y's are kind of right given the X's. Still, it is not a good enough model on its own. It only takes a little tweaking of the input parameters to enable us to get accurate results from our coarse model. The input mapping is key. How we go from our X's to our X primes. This idea was originally developed by Dr. John Bandler of McGill University in 1994. The reason this works is that the coarse model has the key dependencies. In fitting this surrogate model now, the coarse model with the input space mapping, only the parameters of the input mapping need to be adjusted. This is a simple task as there is little interrelationship of the input parameters. They have weak correlation. We can use this to develop optimum designs, with an enormously large number of unknowns. So the coarse model is a model that could be used with very many dams in this case. It gets the essential correlations and nonlinear relationships right, and it could perhaps apply to nearly every dam in the world. The input mapping, which is very simple to develop, would be customized for each dam. Now let's get back to our picture of dancing ladies. Here are dancing ladies, so it's pretty easy to see that they're dancing. This is certainly not abstract. But this is an abstract representation of dancing ladies. At least that's what I see. I'm not too sure what you see, but I think this looks like dancing ballerinas. But it doesn't have a lot of detail, does it? It has an approximation to the dancing ballerinas. I believe that this type of painting links into exactly how our brain works. This is our coarse model of dancing ladies. We've bypassed that input mapping that I'm sure the brain uses. This painting and many abstract paintings short-circuit the way the brain works. We can apply these ideas to engineering systems. This is a survey-like paper that Paul Franzon and I wrote with our graduate students on how we can use surrogate modeling with circuits and systems. And we can apply it to many other problems as well. I think this is a great idea. Now, if President Obama had thought of theories of mind, I'm sure this is what he would have said. One of the theories of mind is that the human brain is forever trying to fit surrogate models to experiences, continuously refining the model fit. Okay, we're adjusting the input parameters. We anticipate, make model projections, usually without being consciously aware. This is associative thinking. He, she, or it, who, which, holds the most models in his, her, its processing unit, wins. Another idea is self-similarity. Back to number 11. This painting has self-similarity. As we zoom in, we see much the same patterns as we saw before. It appeals to us because this is the way the brain works. We are short-circuiting our inner workings. It tickles our cerebral senses, but in a different way from the painting of dancing ladies. I'm going to show you something else which has self-similarity. This is Newton's cradle. The pattern is repeating once every 2 seconds, and so we say that it has a frequency of 0.5 Hz. This is well behaved, a nice repetitive response. But this is an animation. Here is a circuit that has a nice expected behavior. This is a 7th order filter. This circuit, perhaps constructed another way, is on the other side of the antenna of every cell phone. The input on the left is a pulse of sine waves. Here there are 275 sine waves. The output on the right looks much the same as the input. We see a little bit of ringing, but all in all, much what we would expect. The input here is varying at about 1 billion Hz, a bit faster than the balls in Newton's cradle. It is useful to plot the level of the output as the frequency varies. And that is what is shown here. This response is the transmission of the filter versus frequency. So signals get through if they have the right frequency, but they do not otherwise. This is how we separate different communication signals. Now let's get back to Newton's cradle. That animation is not exactly what happens. Look at this. This is the real response. Things behave a bit chaotically, not nearly as neat as we saw in the animation. What is going wrong? Why does it behave chaotically? Perhaps we should send this back and get another one, but we will have a similar result. This is chaotic behavior. It is how the world works and how the brain works, and how all circuits really have to work. Just in case you've forgotten about the bandpass filter, here is the response we expect from a filter. This is called the steady state view. This is how we analyze and in the end design our radio frequency circuits. But in reality, circuits do not work that way. That is a bit of a heresy, but if we open up our minds we can understand many things that confuse us now. How noise arises in circuits, how electromagnetic fields in circuits interact, sometimes. Again, this is the nice, neat response, but let's look at what actually happens at the output. We do not get just one pulse of sine waves coming out. We get what looks like echoes. It looks like a chaotic mess. These are simulated responses, but we have done measurements as well and the behavior is much the same. It is very difficult to do these measurements, and that is why others have not looked for it. Why would you look? You only expect one RF pulse at the output. The interesting thing here is that this response is the deterministic response of a 14th order differential equation. This looks unusual to us, as our internal models, what we think, must be a reduced order abstraction of the real world. Another conversation, and too deep for today, is that this behavior is behind flicker noise or 1/f noise, something we see throughout nature. Jackson Pollock captured that. Chaos. 1/f behavior. Self-similarity. He tapped into the way the brain works. It ties into our cerebral sensibilities. I believe that what I have just talked about could really change what we do in engineering. As engineers, we develop reduced order abstractions of the real world. This is my greatest idea. Where do ideas come from? As engineers, we develop engineering abstractions. We build on existing modeling concepts. We go from physics, chemistry, mathematics to models. We create high-level order out of complexity. At the fundamental research level, we do not build widgets. We develop the ideas that enable widgets to be built. Electrical engineering is grounded in physics. We model, experiment, abstract and repeat. Many people, especially lay people, see fundamental research as a path to a goal. Some see it as climbing a mountain, and when we get there we have finished. But fundamental research is more like digging a hole. Where the ground is soft we keep digging. If it is hard we move on. Research is really like shooting first and then drawing the target. Do not get stuck in the rut of looking at just one approach. As in everything, diversity of ideas is essential. You must travel, confer, read a lot, and think. Look at things from different perspectives. You need to take risks, but not all of them will work out. You need to be exposed to a lot of ideas. Do not compartmentalize the ideas that you pick up. You need to think and let those ideas ferment. Let ideas come together. New ideas are the synthesis of other ideas. This is not an original concept. Many people will say the same thing. New ideas are mostly, perhaps always, the synthesis of ideas you have been exposed to. You need to be exposed to many and absorb many. I want to share with you some of my academic history. I received my bachelor's degree from the University of Queensland in 1976. This is the University of Queensland. It has 48,000 students. This is the most beautiful campus in Australia. I received my PhD in 1983. Now, a PhD is not a natural state of being. It changes the way you think and tackle problems. With rare exception, you need to be apprenticed to gain the necessary skills. My advisor was Peter Kahn, and he and I are descended from a long line of academics. Lord Rayleigh is a rather famous individual in electrical engineering circles, and then he received his PhD. So these are all my ancestors. I can count Isaac Newton as one of my academic ancestors, and also Galileo. And the lineage keeps going back. Tartaglia was a self-made mathematician. Which brings me to the story of a rabbit who was doing a project. The title of the project was "The Rabbit is Smarter Than the Coyote, the Wolf and the Fox Combined." The rabbit was outside his burrow, eating grass, and in turn came along a coyote, a wolf, and a fox. When the coyote came along, the coyote said, "I'm going to eat you." But the rabbit said, "No, you cannot eat me. I've almost finished my project on how the rabbit is smarter than the coyote, the fox, and the wolf combined." And the coyote said, "That is stupid. How could that possibly be so?" And the rabbit said, "No, it is true, it is true. Let me go and show you." And the coyote said, "Well, I'm curious, and I'm hungry, but I'll let you show me, and then I'll eat you for lunch." The rabbit and the coyote disappeared down the burrow, and a little while later the rabbit is outside again, munching on grass. Beautiful day, beautiful sunny day. And along comes a wolf. And the wolf says, "I've got you now. I'm going to have you for lunch." And the rabbit said, "No, you can't do that. I've almost finished my project on why the rabbit is smarter than the coyote, the wolf, and the fox combined." And the wolf says, "Oh, that's rubbish." And the rabbit said, "Well, let me prove it to you." And the wolf said, "Okay, but then I'm going to eat you for lunch." The rabbit and the wolf disappeared down the burrow, and a little while later the rabbit's outside, eating grass on the bright sunny day. And along comes a fox. The fox grabs the rabbit, and the rabbit says, "Stop, don't eat me now, don't eat me. I've almost finished my project on why the rabbit is smarter than the coyote, the wolf, and the fox combined." And the fox said, "No way." And the rabbit says, "Let me prove it to you. Come down to my study and I'll show you." And the fox says, "All right, but then I'm going to eat you for lunch." The rabbit and the fox disappeared, and a little while later the rabbit's outside, munching on grass. And along comes his friend the bunny. And the bunny says to the rabbit, "Mr. Rabbit, aren't you afraid to be outside eating in the open? What if a fox came along?" And the rabbit said, "No, that's okay. I just tell them that I'm working on my project, that the rabbit is smarter than the coyote, the wolf, and the fox combined." And the bunny says, "Well, Mr. Rabbit, I know you're really smart, but I don't think that's right." And the rabbit says, "Well, let me prove it to you." So they go down to the burrow, and as their eyes adjusted to the dark, they see a pile of bones. And the bunny says to the rabbit, "Mr. Rabbit, who's that?" And the rabbit says, "That's my advisor." The moral of the story is, the subject of your project does not really matter. What really matters is your advisor. When we teach, we want to train our students to think. To do that, we, as faculty, must be thinking one or two steps beyond where we want our students to be. That is one reason we do fundamental research at a university. But we must also be good stewards of the resources invested in us. We are in a special position to solve societal problems, and we have shown that we've been able to do this many, many times. I wrote a textbook to capture many of the ideas I had. I could not think of a better way to spread the broad knowledge I've acquired over the years. Albert Einstein said that scientists investigate that which already is, engineers create that which has never been. James Michener said that scientists dream about doing great things, engineers do them. It is great to be an engineer. I feel that life has come to me very quickly. There is so little time to do it all. I am humbled by the honor you have bestowed on me. I hope that I can continue to be a good educator, a good researcher, and continue to contribute to our nation's and the world's security. I leave you with my most powerful ideas.